Hi everyone, greetings from India, and I believe you guys are keeping safe. It's a very different way to present my research to uh, all of you, but I must admit that this have actually made it possible to share my research with you. Most of this presentation comes from one of my earlier presentation at IACA in Ahmedabad, and I'm glad that because we work in different areas of specialization, I wish that this presentation will help us put the pieces together and see how our research work adds up. As we understand that the main driver in the Sun-Earth system is the north-south component of solar wind magnetic field, which is called IMFBZ. But beyond IMFBZ, which remains the primary driver, what are the other factors which drives the coupling between magnetosphere and ionosphere will be the focus of this talk today. My collaborators with which we have worked together for the last couple of years to bring this research to you. The first thing which comes to our mind when we talk about any space weather event and its effect is the distribution of charged particles in the ionosphere. And the distribution depends on the drivers which makes the ions or the electrons move in the ionosphere. And if we talk about a quiet time, which means the absence of reconnection or southward IMFBZ, from the top side, the things which drives this distribution can be the solar wind pressure, and then the solar flux and solar flares also. So they also are known, all of these are known to cause changes in the distribution of charges in the ionosphere. And from the bottom side, as many of us know, atmospheric tides, volcano, gravity waves, SSW, seismic activities like earthquake, tsunamis, they can potentially redistribute the charges in the ionosphere and brings changes in the effect of space weather event. When most of these drivers are very sporadic and then nature is not very well known on global ionosphere, some of the periodic drivers like atmospheric tides makes the charges in the ionosphere move with regular periodicity. And here you can see, for example, how the atmospheric tides makes the ions move in the vertical direction in the ionosphere. This plot shows the diurnal variation of ions over Hickamarka as modeled by Charles and Fair from Hickamarka radar data. Unfortunately, we do not understand the nature of other drivers as well as we understand this. Similarly, the disturb time drivers includes from the top side are prompt penetration electric field, which happens because of the southward turning of IMFBZ, which creates a penetration electric field and which travels through magnetosphere and then to high latitude polar region, and from there get transmitted to the global ionosphere in no time. So this prompt penetration of the solar wind electric field is called undershielding condition, when our Earth's ionosphere is not shielded very well and this field penetrates. And as soon as the PPEF gets withdrawn or the southward IMFBZ turns northward, we have overshielding field, which is basically absence of PPEF and which behaves just on the opposite direction, which opposes this penetration electric field. The next one is called disturbance dynamo, which is basically happens because of Joule heating over the polar region. The neutral wind circulation changes, which because of dynamo effect creates a field which again penetrates to lower latitudes up to equatorial latitudes. Now these two fields have been studied and modeled by Fair et al. 2008, and their nature, at least qualitatively, and up to a great extent quantitatively also have been studied here as shown in this figures. And we also have Substrom as the disturbance time dynamo driver, and we'll talk about it in the next couple of slides. When the previous drivers are well known and have been talked about by many researchers over decades, two drivers which are not very well spoken about are Imfpy and its effect on global ionosphere, which is nothing but the east-west component of the Sun's magnetic field, and polar boundary intensification or bulky burst flows. It's basically the earthward flow from the night side, which is believed to deposit huge amount of mass, energy, and momentum into the polar ionosphere. The people working in magnetosphere would know much more than me because I studied this only in connection with its effect on ionosphere. So I would suggest you to go and get some more knowledge about this. So talking about Imfpy and its effect, usually when IMFBZ is southward, or when we have a connection, we have region 1, region 2 currents over the polar region, which creates the TP2 cell pattern or convection cells for plasmas, or you can say potential contours over the equatorial region. Now, during prompt penetration, this potential contours expands over the whole globe and reaches up to equatorial latitudes. This is purely the effect of IMFBZ. Now, from radar study, what we know from Superdun radar study is that the convection cell patterns get distorted or twisted because of BY effects. Now, when BZ is northward, we do not see substantial movement of the cells or strengthening of the cell as seen in the top row here. But as soon as BZ turns southward, or we have a disturbed time condition, very two strong intense cells are formed as shown in the second and third row here, and depending on the value of Y, these cells get twisted clockwise or anti-clockwise. This is kind of well-known effect of IMFBY over polar region. But extending the effect of BY beyond polar region, it's very sporadic study have been made on this. One of them, or one of the earliest I would say, is this one, where you can see that during this around soon after 1 UT, our BZ is turning northward, and when you expect a overshielding field and the electrical field over Hickomarca, which is shown in the bottommost panel, should flip, but instead there is a delay of 30 minutes. If you read the paper, you'd know more. There is a delay of 30 minutes, which they explained on the basis of change in sign for BY. This is one of the earliest study on BY's effect on low latitude or equatorial latitude. Moving from this, we have another strange anomaly reported from CHAMP-TC analysis by Menucci et al. 2008, where they studied number of very strong geomagnetic storm and the TC variations. And what they observed is this, particularly 20th November of 2003 storm, which was much stronger than the rest of the storm, did not show much TC in comparison with other storms like October 30th or even October 29, 2003. They followed the study up, and in 2014 they came up with another study where they showed that in many similar storms, in spite of having weaker in comparison to this one, weaker DST values, they found that the TC values for this particular storm is not very high. The unique thing which they found out is during the commencement of the storm, particularly on this episode of 20th November storm, the IMFBY was hugely positive, and they concluded that one of the possible reasons could be the high BY value during the commencement of the um, storm. Moving on, in 2017, we published a paper where we showed that during a storm time, which is shown on top is IMFP-C and CMH, during a storm time, usually in the opposite side of the Earth globe, which are called antiportal points, you will expect opposite polarity of electric field, um, which is shown by Kelly 2007 here, that even during storm time, India and Hikamarka, which are on the opposite side of the globe, maintains opposite polarity of electric field. But during this episode of 7th January 2005, we noticed that both Hikamarka and Tumba in India are showing same polarity of electric field. Now this was very intriguing, and on doing little bit of digging, what we found that if we extend this model of Rouhani and Greenwald about the polar region circulation of these convection cells, we find that the expansion of the potential contour from polar region to equatorial region, if it happens in such a way that both the station, which are antipodal in nature, get covered within a single cell, they can possibly show same same polarity of electric field, and this is what we believe has happened on this event. This has been explained and supported by a lot of other data sets also, like super-dendrite dataset, and more importantly by super-mag observations, which we took from polar region to equatorial region, and we showed that antipodal point on the polar region at high latitude, which were anti-correlated, but as we move towards the equatorial region, which is shown in second last row, we see that the stations are in sync with each other, which tells us that the current direction are same over these stations, which gives us confidence in saying that these stations must be under the single potential contour cells. That's why we see same direction of electric field over them. We did some modeling effort, which is still ongoing. We are in the process of submitting this, and we discovered that even from modeling studies, we see that IMFBY can greatly influence the drift and even neutrals over the whole globe. Moving on from IMFBY to Substrom, what we see is there is a controversy. Some people, some researcher reports that Substrom causes a eastward electric field in the day side, whereas some researchers like Kikuchi and Hashimoto, they found that the substorm can cause westward electric field in the day-side ionosphere. Now this controversy is quite old, and we were searching for an answer, and along with the polarity of the field, what is their comparative role during the storm time vis-a-vis IMF BZ driven PPEF. So we took up two events from different data sets, and what we found is sometimes the substorm can actually induce eastward electric field over the day side, and it can even enhance the already existing tidal field and PPEF, which are also eastward during the daytime or in the dayside ionosphere. In contrast, in other event, we found that substorm can also cause westward enhancement of equatorial electric field, which will now oppose the tidal electric field, which is usually eastward during the daytime, and also the PPEF, which is also eastward during the daytime. So we see that our research shows that substorm can cause both eastward and westward electric field in the day side, and hence it can sometimes enhance the resultant electric field, which is nothing but the superposition of all the fields which are driving the electrons or the ions in the ionosphere, and sometimes it causes westward electric field, so it will reduce the effect of PPEF and tidal electric field. The last topic is Earthworm Plasma flow as a driver for global ionosphere. Now this is a very rare study we have come across. What you're looking at is, in red is shown LANL particle injection data at the geosynchronous orbit, which is in the midnight sector, and on the top row you're seeing in blue is high latitude AL values, and we see that the AL variations quite closely matches with the particle injection data. And the bottom panel we are seeing the same LANL data along with the drift values measured at equatorial latitude by Hickamarker radar. And what we are trying to show is their correlation, and their matching, the peaks matches very closely with each other, and the idea is that this particle injections is driving this changes in the electric field which we are seeing up to equatorial latitude in absence of similar variations in electric field of solar wind or pressure variations, as I will show you in the next slide. In this slide we are saying that the electric field of solar wind, the pressure, and the GOES satellite, which is in the morning sector, are not showing this component of periodic variation, whereas the LANL flux, the particle data, which is at the night side, magnetometer data from Huancao, and drift data at Hickamarker, they are showing this periodicity. So we are concluding that possibly the plasma flow is generating some parallel electric field over the polar region, and under strong coupling because of southward Imfpy between high latitude and low latitude, this extra field is getting transmitted to low latitude where Hickamarker is recording it, or Huancao magnetometer is picking it up. I'll summarize my talk with the following points: that we must recognize other factors for driving the charges in the ionosphere other than Imfpy. We also should develop at least qualitative understanding of the nature of electric field that each of these drivers can produce and drive the global ionosphere. The equator is exposed, contrary to the general belief that equator gets affected only by southward Imfpy. The equator actually gets exposed to all the driver during storm time if Imfpy establishes a strong coupling between high and low latitude. And lastly, we need to account for all the drivers acting simultaneously, which superimpose to give the total field acting on our ions and electrons during a space weather event. Thank you for your patience, and I appreciate any question. Thank you.